Hello everyone, my name is Hayden Easton, and today my S&T topic will be on thermoelectric coolers. So starting off with the history of thermoelectrics, the first and the most important governing principle that enable thermoelectric coolers to be a thing is the Seebeck effect. We've studied this a little bit in previous classes such as instrumentation, but mainly it was discovered by Thomas Seebeck on the left, and it deals with voltage being created whenever two dissimilar metals are in contact at different temperatures. So he figured out that, Seebeck figured out that there was a voltage potential difference across those two wires, and the next guy, Gustav Magnus, pictured in the middle, he figured out that the change in voltage was actually proportional to the change in temperature, and it was defined by a constant that's based on the metal compositions that are attached to each other. The last and third guy was John Charles Peltier, and he discovered that instead of having two metals at a different temperature that create a voltage, you can apply a voltage and get metals at different temperatures. So, as I stated earlier, that Magnus, he had discovered that this alpha coefficient is used to determine the voltage created from the different temperatures of the metals. And Lord Kelvin, or William Thomson, he discovered that using Peltier's developments of applying a voltage and supplying a current to those metals to make heat transfer, he discovered that the heat is absorbed or removed when a temperature gradient is present in the two dissimilar metals. And that heat transfer, again, is also proportional to the temperature gradient and the supplied current. So the thermoelectric coolers here, it is a solid state cooling method. So basically there's no moving parts, there's no convection, everything is done through conduction. So like I said earlier, instead of having two temperatures at a different temperature and getting a supplied voltage, you can supply a voltage and current will run through these plates, and the Seebeck effect will allow the heat transfer to occur. The best way that I had this explained to me was that imagine you have like a metal wire and you heat one end of it. All the electrons, they get more kinetic energy and they start bouncing around the wire, and they want to push the other electrons to the other end, and that's what electric potential or voltage is. So when you have one metal at one temperature and another metal at another temperature, and they have different electron densities, ultimately there will be a loop that's formed, and that's how them being at different temperatures drives a current, or you can drive the current and have heat transfer occur. So in this case, they have the cold end and the hot end plates. So on this side, you'll have the environment that you want to be extracting heat from, and it will ultimately be dissipated on the hot end plate to the environment. So up here, you can see a picture of like a little 1.5 inch by 1.5 inch Peltier cooler. And you can see from the previous slide, those N and P junctions or the N and P semiconductors that are used to drive the current. You can see a ton of them in there, and those are ultimately what the current is flowing through to allow the heat transfer. So there are plenty of junctions added between the two plates to increase the number of locations for heat transfer. And the most common way that these things are used is in a configuration like this, where you have some cold air that's circulating, or fluid in any case, that the heat is taken away from and it is ejected to the environment. So some of the common uses for a Peltier cooler or a thermoelectric cooler is small refrigerators and wine coolers, electric portable food and beverage, personal and portable AC, cooled seating, and cooled coverings such as blankets. So in this case, you can see that they have fins, and they also have fans to adjust the circulation of the external airflow, as well as the N and P junctions as previously discussed, so that the current will flow through. And the main reason for these things being, we have the pros and cons here, is that they're best for small spaces. The other alternative to this, like say for a refrigerator, is for people to use a big compressor or something that's typically has more capacity, but comes at other expenses. But this one's good because it has small spaces, or it can fit in small spaces, such as like these portable devices that you're carrying around. You wouldn't want to carry around a compressor or anything. And there's also less moving components, which means there's a longer life and less repairs, because typically the moving components are the ones that experience wear or need to be replaced. And as Alex had mentioned, this process doesn't use refrigerants, so there's like HFCAs or whatever, the hydrofluorocarbons, they are harmful to the ozone layer, so this is a good alternative to using conduction to accomplish that. Cons, they're costly when used on small spaces. You have to imagine that picture up there with the surface area, that you'd have to enlarge that a bunch, and it's expensive. And also, it is entirely dependent on the ambient temperature and the humidity of the surrounding air. So if your environment is closed off, you wouldn't want to just pump heat into that. You could cause all sorts of problems pumping too much heat into something that's not monitored. And in conclusion, thermoelectric coolers are an environmentally friendly option that can be used to monitor the temperature closer than other alternative methods. It's pretty fine temperature control. And it's also a good option for solid state cooling when you don't have the setup or the equipment to supply cooling fluids or compressors. And they're relatively simple to understand. Besides the Seebeck effect, you can just apply a voltage and you'll ultimately get a proportional heat transfer. Here are my sources. Any questions? No? Thank you.